Relax my eyes, I see flashing lights and I'm not alone. Are you alright? On the other side, I can feel you close. I feel alive, hear the drums get high and the bass down low. Open your mind, we could dance all night.
Good morning, everyone. I love Doc because it gives a great platform to share ideas and connect with collaborators across the ecosystem. And in that spirit, I'm here to share a little bit about why EDA is strategic and important for Google, and how we are optimizing EDA with the help of Google Cloud. I said I love Doc. I also love my job. All right, it's clicking, but the screen is, there we go. I also love my job as a product manager for EDA in Google Cloud. I think my primary responsibility is to make sure the end users don't have to worry about infrastructure, so they can focus on the core processes, building the IP, and the things that matters to them most. I also love my job because it gives me an amazing opportunity to work with collaborators across Google Cloud, and gives me an opportunity in a forum like this to talk about what many teams have contributed to making a product and a capability like EDA successful in Google Cloud. So the way we do that is, as you know, as Google as a company, our mission is to help organize world's information. So similarly, from an EDA standpoint, in the high-performance compute world, we want the most comprehensive, capable system accessible for users across enterprises of all the sizes. Let me just give you a little behind the scenes on why EDA is important in the context of Google. So for example, you may agree with me that the agentic revolution is upon us. What is actually driving behind it? As you can see from all the innovations we were able to drive out of Alphabet, going back 10 years ago, All these algorithms allowed us to get to a point where the LLMs are powerful enough to be able to start driving the agentic AI revolution. And behind all of these algorithms, all these transformer models is also kind of the growth in the underlying algorithms itself, the complexity of it, the number of parameters it's needed. And as a result, there is an exponential relationship between the complexity of your transformer and the amount of petaflops scale compute or exaflop scale compute you need to be able to come up with these models. So 10 years ago, when the researchers started working on early versions of these models, they figured out quickly that it is a hardware-software co-design problem. In order to be able to build models that are more complex, more performant, and more useful, you also need the underlying compute platform that would support developing these models. So as a result, we have made investment in our own accelerator called Tensor Processing Units, or as you may know them as TPUs. And as a result, combining the algorithms and the models, we were able to bring a lot of TPU-driven innovations like the AlphaFold, like Gemini, like Veo. I mean, this is really an exciting point in time in the industry. The folks at DAC, especially the Exhibitor forum, they run a very tight ship. I had to send in these slides ahead of time. And in the meantime, we already have Veo number 3. So the pace of innovation is so fast that in a matter of weeks, the slides are going out of date. So let me just give you a little behind the scenes on the TPUs that the teams use to train these models and come up with these innovations. So the EDA optimization story I want to talk to you about is how do teams involved in building something like our 7th generation TPUs have run their EDA workflows using Google Cloud technologies that allow them to tape out a successful chip like this, and also have a forward-looking roadmap in terms of how they're continuing to grow the complexity and capability of our TPUs. I'm just using this as an example, even though across Alphabet, a lot of teams use Google Cloud for their own internal EDA uses, be it your favorite Pixel devices or across the Alphabet companies, including folks like Waymo. Can I go back to one slide? Thank you. So the business requirements. So now put yourself in the context of the team that's managing the EDA environment for the internal hardware users. You probably now have a good understanding of the business requirements they are dealing with. So I showed you the map of the TPU-driven innovations, the models, and kind of algorithms that drive the innovation behind the models, right? So the business requirement really is, how can we develop more of these TPU chips in parallel? And going back in time, like 5 years ago, the teams are growing geographically. So how can we also support a multinational team involved in a project like this? And at that time, they were like any other existing EDA environment. So our EDA tools were running on-prem type environment, using LSF as a cluster. But the team really understood the transformational opportunity their end customers have to go through. And in turn, they decided to transform and innovate the way they work. And they choose to start using Google Cloud for all of their EDA needs. It was not done overnight, so they took a phased approach. For example, they would start with burst scenarios in order to avoid missing a tape-out deadline. And then they quickly found out that the burst can be done more like an end-to-end workflow when they start with DV workflows for digital verification workflows. And once they got comfortable using cloud for all of DV workflows, they were able to migrate their entire EDA workflow to Google Cloud. So taking a phased approach. But in the process of doing that, they've also incorporated a lot of EDA-specific knowledge and way of doing things in cloud. So I'll just introduce few concepts. I can go into details of them maybe after the talk if you come visit us in the booth. For example, the EDA environment runs with what we call a hermetic job. So one way of optimizing the EDA workflow is the hermetic job capability allows you that as long as your input parameters for running an EDA workload is the same, you should expect the same results coming back. It's maybe a simple statement made, but it's very hard from a technology standpoint to ensure when you rerun a job with same parameters, you're guaranteed to get the same outcome. So we are able to implement hermetic jobs that allows us to better handle the data management aspect of our EDA environment. So second, for example, the idea would be to share minimum amount of data so that you're not relying on a single volume or a single file system, but really take advantage of the full distributed aspect of data management in Google Cloud and share data only when you have to. And as a result, you can minimize things like the I/O contention and also kind of reduce the round-trip latency. So if you think about bottlenecks to get an optimal EDA workflow, it starts with something like your compute. Once you optimize it, it becomes storage, and once you optimize it, it could be network, and then some combination of it. So kind of systematically working through and coming up with optimizations across all these three levels. So as a result, in a matter of just 2 years or 3 years, they were able to bring all of their EDA workflows into Google Cloud. And as we stand, this environment now runs on more than 250 GKE clusters, running more than 500,000 cores, like 500,000 cores at a sustained basis. The way we have set up the environment, we also allow a lot of data sets. So we are able to generate more than 200 million data sets and also optimize our EDA workflows further by learning from those data. So let me just give you a little bit details behind how this is all set up. So now this is what we call EDA Cloud. EDA Cloud is our internal EDA execution environment. It's not a product from Google Cloud. And as you can see here, this is purely a cloud native architecture. And this is not a kind of a cloud solution architect pulling together what is possible in cloud. The TPU chip that you saw runs in a production environment that uses this architecture. So this is battle tested, ready to use in a production environment for mission critical chip design environment. I'll just highlight a few of the key points here. So for example, starting with the durable cloud session. So if you are an EDA user, you started your day, you had your personal laptop or a machine, and the durable cloud session ensures that as soon as you log into your machine, a cloud workstation is ready for you, available to start doing your job. And as you did all your work in a cloud workstation and you're ready to submit a job, there are three things that happens. One, we use tools across all the major ISVs, and we manage the tool version. So it's a very kind of understandable pain point that at a time you may have thousands of these tool images, if you especially don't want to change the tool version number as you go through the project. So all of those tool images are available in persistent disk. And when the job input comes from the user in terms of where is the input file is located, what tool version they want, and how they want to run it, it's all brought into our containerized job environment where the tool gets mounted, the input file gets fetched, and the job gets executed in a GKE cluster. Once the job is done, there are three things we do. As the job is running, the user can interactively log into the worker node. If they have to real-time debug and understand what's going on, they can get that information. And second, in most of the time, you may not be looking at the full simulation result that is coming back. Maybe you're interested in key data points from the message file. So we are able to parse those and put that in BigQuery so that it's easier for running analytics on top for the users to quickly understand what they need to focus on resolving in their study that they're doing. And finally, the job files that get generated it gets archived into GCS buckets, and we have the ability to kind of go back and audit and retrieve them when you need at the later stage of the time. So again, right, so I just wanted to share this part of the story to kind of explain how we are running our TPU EDA environment, the EDA environment to support the TPU development. So if there is like a takeaway on is Google Cloud really ready to run your mission critical EDA workloads, the answer should be very clear. Yes, we are, and we've been doing this for many years now. And what is really enabling, this goes to the next part of what I wanted to talk about, which is like how, from a high performance computing standpoint, we engage and enable these teams, is the investments we've been continuing to make from a high performance computing standpoint for many years now. So starting with from the compute layer, we have Intel, AMD, ARM, and NVIDIA-based chips available in the compute platform, so that as an EDA user, depending on the tool, depending on the workflow and the job, you have the choices available to optimize, whether it is more compute optimized instances you need or a memory optimized machines you need to run your problem more effectively. So from an optimization standpoint, it starts with optimizing the infrastructure layer at a compute level. And second is, I shared a lot of details around our internal execution environment, which is containers based. And they got to that point through like a transformational journey. It may not be the answer for everyone. So you may choose to keep your on-prem environment and may want to run things in hybrid, in cloud. You may have made choices in terms of storage and other capabilities that you may like that works efficiently in your environment. So we want to provide compatibility from a high-performance compute portfolio standpoint. So from that perspective, kind of we have, as a part of the HPC portfolio, we have a number of the underlying storage and schedulers, compatibility with the tools and partner ecosystem required to meet you where you are to run your EDA workloads in Google Cloud. I want to highlight maybe two things from this portfolio that are new announcements from Google. The first one is our HPC optimized AMD-based virtual machine. We call it H4D, and it's AMD 5th generation based on the Turing platform. And when we compare some of the performance coming out of the H4D compared to the previous generations of AMD, we are seeing a very high performance boost, and we think that's going to be crucial to meet some of the stringent compute requirements in the EDA. This is something we announced in April, so this is in a preview, which means you can scan the QR code, sign up to be part of this program, and once you sign up, we can give you access to H4D free of charge in a non-production environment as long as we are in the preview phase to allow you to test to see how it would fit with your expectations on compute platforms in cloud. So when we talk to customers, they express cost as one of the primary drivers in choosing cloud. So our approach to close the gap in terms of driving economics that's comparable to on-prem is through something like H4D, which we believe will give the kind of the right economics customers are looking for to run their EDA jobs in Google Cloud. In addition to more CPU-based compute, there are also a lot of EDA tools that are now GPU-enabled, and growing our portfolio of NVIDIA-based GPU offerings. The A4X is going to be our most powerful GPU out VM, and that is also coming soon, and as we speak in this quarter. So as we talked about some of the compute platforms and cost as a kind of the key driver, I wanted to kind of highlight few of the levers you have as a customer to be able to control the way your consumptions happen in cloud, right? So for example, you may be aware of maybe the two ends of the compute spectrum. One is the on-demand is when you need compute resources when you want it, probably going to be the most expensive of all the offerings in cloud. And then the other end of the spectrum is the spot VM, which is excess capacities that are available that are deeply discounted, but they may be taken away when we need the capacity for a customer who may have requested it or reserved it. So this is where we have introduced a newer model called dynamic workload scheduling. This is available for GPU-based instances, and we will be rolling out when the H4D CPU-based VM is also available through this mechanism. So what it really is, this morning when I requested an Uber to come here from Los Altos, Uber said, this is your fare if you want the ride now, and then I'm going to drop you 10 bucks if you can wait 10 more minutes before I pick you a ride. It's kind of similar to that, where if you run the rightly regression and you're kicking it off on Monday evening and you want the results back Tuesday morning, you may want to go with a small percentage of spot, but then maybe a reserved and committed instances, so you're guaranteed to get that result. But let's say you're triggering the same job on a Friday evening, and the engineers are not going to look at the result until Monday morning. You have a window of more than 48 hours to get that 12-hour job done. So think of dynamic workload scheduling as a signal you would give to us saying, I'm willing to wait for my results over a period of time. I want a guaranteed output in that period of time, but I don't want to pay as much as like what I would get in a committed discount or a flex cut. At the same time, I don't want to lose the reliability if my instances were to be taken away from a spot instances standpoint. So this is where we think if you're especially looking from the model of dollar per job of getting the work done in EDA, as opposed to cost per core hour, we think we can meet better economic proposition through the dynamic workload scheduler. So the story I've shared so far is more about more classical kind of infrastructure as a first order problem to solve. But we can also go beyond that. For example, the way we see HPC evolve, especially in the context of EDA from Google's standpoint, is we have capabilities coming across multiple parts of Google divisions, whether it's research, DeepMind, Alphabet's own internal use of chips, as well as other parts of cloud, whether it is security or from our Vertex AI and data analytics part of the portfolio. So we feel that we have the opportunity to help our customers by integrating all of these capabilities as they become viable and relevant in the EDA space. And Google Cloud would give you that platform to be able to consume the number of innovations that's happening across the cloud. So for example, in addition to the CPU, GPU, and maybe even the TPU platform in the context of EDA, as we make investments and quantum becomes more of a practical application here, you'll be able to consume that through kind of the Google Cloud's capabilities. So in a nutshell, like some of the key takeaways I want to leave you with, right? So one, if you're looking for a fast and affordable way of running your EDA environment in Google Cloud, I've shared some of the mechanisms we are allowing you to be able to do that. Second, we are also making it easy and compatible with some of the tools that you're already using, because in most cases we run those tools as well. And finally, we do this in the context of working with other partners in the ecosystem. So this is working with top ISVs, as well as schedulers and system integrators who are involved in the ecosystem. And finally, it gives you an opportunity to leverage the best of Google Cloud beyond consuming the infrastructure, to be able to leverage and work with the teams that are working on things like the Google Research and Alpha Chip type capabilities. So in order to continue to be informed on what we are doing, one of the things we are doing is, this is more of an industry community. It's not just Google specific, but we have started and also included partners and others in the ecosystem. So I would encourage you to make a note of the QR codes here that allows you to see what we have done from a Google Cloud Advanced Computing Community series of events in the past, as well as join the QR code to be part of the future programs we have to stay current on like what we are doing in this area. And finally, I'm happy to go through additional details behind the concepts we walked through. And there are also a number of Google experts at the conference, so please do come talk to us either after the talk or at our booth. And for any ongoing conversations, Carl and Piyush, who are also at the conference, my wonderful colleagues, they would love to hear from you if we can take the conversation further and go on this journey with you. Thank you.
All right, that concludes our session. If you have any questions, you can speak to him on the side or at their booth. Next up at 12 o'clock, we have Leveraging AI to Boost Productivity and Quality of Results in the Digital Design Creation Flow. Ankur Gupta with Siemens.